about that one. For the pure resistive load for the half wave rectifier, the circuit will be like this. So this is the input voltage, or the diode is here. The load is your load, and you know that for the positive half cycle, is for the positive half cycle of the input voltage, this diode is on. Diode is on. Diode on. So output voltage is must be equal to PS. That is why we will get that this one here, some same. And for the negative half cycle, the current is 0. To turn off any power electronic device, the condition is that it must be equal as well as current must be 0. So at T equal to 5 or T by 2 half cycle, the current is 0. And then of course the diode will be off and there will be no current, so we will not get any voltage here. And also the and the VDC and VO will be your VM by 5. If we represent V as the source voltage, Kn sine of omega t, that is VS sine of omega t. So VM can be replaced by root 2 VS by 5, and it will come as 1. Okay. You have to communicate with me. Is it okay? Can you hear me?
Yes, sir. We can hear you, sir.
Good. And then we have described that this circuit. I'm just reviewing because the midterm we have covered it, maybe we have forgot. So I'm reviewing. This is the RL circuit. And this is the, sorry. This is the L and this is the R, and we are taking the output from here. So if we start from here, this is the input voltage. This is the half cycle. This is the full cycle. Current will start little lagging here because this is the inductive load. The current will not, because starting at the starting, omega t equal to 0, t equal to 0, the current was 0, so it will take some time because of the change of current with respect to time. That will oppose, the inductors will oppose this one. That is why the slag is starting, and it is going like this, and we have a peak value somewhere here.
Sir, a
yes.
constant noise is coming from your side.
হ্যাঁ স্যার একটা মানে আওয়াজ আসতেছে একটু মিউজিকের বা কিছু একটু কনস্ট্যান্টলি আসতেছে
Music, it is not from my side because my room is totally empty. Some of you
Sir, maybe এটা ফ্যানের আওয়াজ হতে পারে, স্যার।
fan, okay.
Mute everybody, maybe.
Okay. Now, are you getting the
No,
sound?
sir, it's all right.
না স্যার এখন ঠিক আছে
Okay, because of the fan has the age of almost 14 years, and it is giving sound. Okay, let me turn on my AC. Okay, it's clear now.
Yes, the sound has stopped.
Okay, now so the current will. My voice is okay.
Yes, sir. Your voice is
Yes,
okay.
sir.
Okay. So current will have the peak value here, and the current is supposed to stop here in the half cycle because the voltage has gone to negative voltage, but because of the inductors it stored the energy, so it will continue to flow. That means the diode is not stopping conducting even the voltage is 0 here. It will continue to flow. That means diode is conducting. The diode is conducting up to until this time. And the the crossing of the VS and VR will be crossing of VS and VR will be at the peak value of the current, right? Peak value of the current. Why?
Yes, sir.
Because if when the diode, if the current is there, so diode is conducting, we can always apply the Kirchhoff voltage law here plus real. So at the crossing of Vs and VR, Vs must be equal to VR, right?
Yes, sir.
If you substitute here, then VR equal to 0, L di by dt equal to 0. So di by dt must be equal to, so di by dt is nothing but the change of current. Look here,
Yes,
change
sir.
of current is constant. It is 0, sorry, not constant, it is 0. There is no change. So that is, and it will maxima. You have probably learned these things in your mathematical class.
Yes, sir. In our mathematics, we have learned.
So then the current stops conducting here, and the Vs will be, VR will be simply I multiplied VR. As long as your I is there, so you have the VR will be here. Right? And what will be the output voltage then? If this diode is conducting, this V2 must be equal to Vs. So let us draw it. Current is going there. So Vs, it is following V. Your VD is following the Vs, and it is going like this, because current is still going there. So VD must be equal to your Vs, and then current stop, and then your VD will 0, and it will continue like this. You understand it or not?
Yes, sir.
Yes, sir.
We have already talked about these things in our before the midterm. So how is your midterm?
Sir, alhamdulillah.
The question was so much easy, right?
Yes, sir.
Alhamdulillah.
Okay, good. And the VL is, because I was very sick that time, I plan to make your question very, very tough. But during that day, probably some of you have prayed to Allah subhanahu wa ta'ala. That is why I become sick.
No,
And
sir, we didn't pray.
then
প্রশ্ন সহজ হবে এই দোয়া করছিলাম ওইটা
We actually hope that it will go easy on us.
yeah, so that is what I just took some of the question from the previous years and set it. Okay, anyway. So I want to plot VL equal to L di by dt. So I'm repeating these things for you for the review, and for the BSCT student, I did not cover. I have taken their makeup class, but this thing I did not cover. So VL equal to di by dt. So look here, the slope of I equal to positive up to this one. So we'll get that VL positive. After the peak value, the slope is negative. So we'll have the negative VL. And exactly when the current stops conducting, so it has come. So this is area A, and this is area B. So in the book, it is already proved that the area will be equal to area B. How can we prove that? We know that VL equal to L di by dt. Then, if we multiply L di equal to VL dt, and if we integrate it over 0 to say T3, then look here 0 to T3, the di, the change of current at T equal to 0 and T3 equal to of course 0, so it is 0. And this is integration of this VL until T3, so we'll have two areas. And it has given in the book. So you try to find it out.
In your last class, sir, you actually showed us the proof.
Yeah, no, I did it for the BSCT now. BSc student did not do that. And if we now think about a constant voltage source as a load here. So this is the L that may come from the source, or there could be some inductance there. And this is your a voltage source as a load. Then the Vs equal to say Vm sine of omega t. So our Vm must be greater than Ed to analyze this one, otherwise this diode will never conduct, right? So look here, until T1, so your Vs is less than your Ed. Am I correct or not?
Yes,
Yes,
sir.
sir.
So of course the diode will not be conducting, it is open. So this Vd will be nothing but your Ed, because there is no current here. So our output voltage will be this one. And then after T1, you look at your Vs equal to greater than after T equal to greater than T1. Vs is greater than Ed, so diode will start conducting. Of course, Vd must be equal to Vs. So then it will be Vs. So it should stop conducting, but because of this inductance, look here, the current will not come, just drop 0. No, it will continue to conduct, and it depends on the value of the inductance, and it stop conducting here. So if the current will have the 0 during a cycle, then we call it discontinuous current. So here current is discontinuous. Of course, here the current will have the peak value at T2, and the zero crossing of this one, Vs and Ed will be this one, because if I again apply the Kirchhoff voltage, the Vs will be VL plus Ed. So at the crossing of Vs and Ed, Vs must be equal to Ed, then VL equal to 0. VL equal to 0 means L di by dt equal to 0, right? So I must have the peak value at the crossing of your Vs and Ed. So that is why the current will have the peak value at the crossing point of Vs and Ed. So the output voltage will go there, until there will be current and this one. And then since the current is 0, then the diode will not be conducting, because already the diode has reverse bias. But since the current did not get any path, so it will force to conduct until the current is 0. So our output voltage will have the wave shape like this. You understand it or not?
Yes, sir.
Yes, sir.
We have already studied this. And if you again plot the VL, it will have the wave shape like this, because up to the peak value, if it is VL, it has a positive slope and it has a negative slope, and this A must be equal to B. You can always prove that one. And before the midterm, actually, we have covered until this one, right?
Yes, sir.
Yes, sir.
Yes, sir.
So now today we shall start new topics. How many students are here? 110. So how many students are supposed to be here today?
Sir, around 140.
140, you look. So 29 students are absent. What happened to them?
Due to load shedding, maybe.
Today there should not be any load shedding, because not many people are using.
Sir, maybe for the weather.
Okay, maybe.
Very sleepy
Okay.
weather.
Okay. So this is the figure. If you look at, this is the figure of these is the figure of practical single phase diode rectifier. Here, look here. This is the source voltage, and the source voltage may have inherent inductance that may come from the source. Oh, you are not familiar with this bridge rectifier, are you?
We are, sir.
You are. Okay. So, okay, let me draw that one for you again. Actually, the bridge rectifier we have taught in the second semester was like this. This is your T1, then this is your resistance, this is your T1. Resistance is your load, this is your T2. And also in the intermediate level, you have probably have learned it, right? And then the current is going this way. And also, therefore, when the voltage will change, so this is your D3, the diode will come back and the current will go there and it should come back here. So this figure is very much familiar to you, right?
Yes, sir.
Yes, sir.
So we shall replace this one, same thing. Just we will replace this one as this way. This is easier to draw. Look here. You will first draw one leg, and then you will draw another leg, and then this one like this. First you draw, then you write down D1, this one, this will be your D2, this will be your D3, and this is your D4. And this is your output load side. So from here you can of course draw a load. And how you connect your supply? This is one leg, and this is another leg, and then you have the supply like this. I have omitted the errors here. And also you can use the filter capacitors to filter out. So this is the bridge rectifier. Okay, we have already learned about this one from the Ned Mohan, but we are just repeating this one. Some students may be bored, and there is always an objection like I am very much slow, and some good students, they are bored. This is not from you. I got this impression from the previous years. Anyway, I am the teacher for everyone, so I have to go in the middle phase, medium, for not fast, medium polar. Okay, look here. This is your VS. Your VS equal to this line. And this is the one terminal of your VS, the another terminal. Negative terminal is connected here. Neutral is connected here. Look here, this is the neutral point they have. From the load side, this is the they put is a P and N. You have to remember this P and N. Okay. So now, suppose for the resistive load, let us think about the positive half cycle. Yes. So this is 5. So now the current, since this is positive and this is negative, current will go here this way. You follow the direction. Current is going this way. Current is coming back this way. Current is going this way. Coming back this way. So look here, D1 and D2s are conducting for the positive half cycle. And now if I apply the Kirchhoff voltage law, VD, so this one not what conducting, this is not conducting, you can find out this VD must be equal to PS. So if I plot this one, this will be VD. And if I, this is the source current. This is your source current. The source current will be the same wave shape of your load current, right? It is a series circuit. Am I correct or not?
Yes, sir.
Yes, sir.
Okay, so if I plot the source current in the different colors, maybe here, the source current will be like this. So this is your, this is the VD, and this is the source current IS, and also that is equal to ID. Okay, for the negative half cycle, okay, I am using now this circuit. Suppose this is resistive. So to understand this one, now the voltage has changed its direction. So the current will go like this. Look here, current will go like this. Is it IS is same direction or it has changed?
It has changed, sir.
Okay, but the current through your resistance
That
here,
is same, sir.
same. So if I say that VO equal to ID multiplied by R, since the current has the same direction, we'll get the same wave shape as your positive half cycle. But the current IS, this is the problem. The current IS has already changed its direction. Look here. Here we have taken the current for the positive half cycle. You see the current was going this way, but for the negative half cycle, the source current is coming back in the opposite way, right? So then the current wave shape will be like this. Say, am I correct or not? Okay.
Yes, sir.
Yes,
If I
sir.
plot the VS here, by T, and the current will have the wave shape like this. This is your VS and this is your IS. So IS current is sinusoidal or non-sinusoidal? Source current? Sinusoidal. Okay, good. So I have defined you total harmonic distortion. Can you remember? Total
Yes, sir.
harmonic. If this current is non-sinusoidal, the total harmonic distortion percentage was IS minus IS square, ISN square, and divided by IS1 square. What is IS and what is IS1?
Sir, could you repeat the question?
What is IS?
Yes, I is the supply, sir. The supply current, sir. That is coming from the source.
Okay, good. So this is the RMS value.
Yes, sir.
And
RMS value. Yes, yes, yes.
What is IS1 then? If it is non-sinusoidal, and then if you have the Fourier series analysis, this is the,
Sir,
then it will have
first,
the first harmonic, right?
Harmonic.
yes, sir.
Okay.
It is known as the first harmonic. Okay.
Yes, sir.
And so look here, since current will have the, for this resistive load, current will have the wave shape of sinusoidal. This is your IS. So your IS will have the same value of IS1 because there is no distortion. It is same sinusoidal, same frequency with your input voltage. Then your IS and IS1 same, and total harmonic distortion will be 0. That means you have not distorted your wave if you use the resistive load. And also there is no phase difference between your input voltage and input current. Is there any?
No, sir.
No, sir.
Okay. So okay, let me define this one here, otherwise I will forget. Sorry. So the input power factor is defined as, did I do it or not? I forgot. In your previous year. Do you know S? and P. What is S from the power system?
S is the complex power, sir.
Volt ampere, right?
Yes, sir. Volt.
Yes, sir.
Okay, sir. Apparent power. Yes, sir.
Apparent power.
Yes, sir.
So, so this apparent power Vs, Is, and then power factor, that must be equal to your power, right?
Yes, sir.
Am I correct or not?
Yes, sir.
Yes, sir.
Okay. Now, since the current is now, current will have that wave shape. Output current will have the wave shape like this is the input voltage. Output current will have that wave shape like this, right? Am I correct or not? Output voltage will have the wave shape.
Yes, sir.
Yes, sir.
Yes, sir.
After, sir. Yes, sir. Rectify.
Okay, I'll define it later because when the current will have different wave shape, then you will understand this one. Otherwise, you will get confused. Just forget it right now. Okay, good. So look at this figure. What is the difference you see in this figure?
There is a current
So the
source. in middle
resistor
of a
has been replaced by a current source.
The resistance has been replaced by the current source. So, and it is load side. This is load side, right?
Yes, sir.
Yes, sir.
So how this can be a constant current source? What type of load it could be that you are
Inductive load, sir.
highly inductive load? Highly inductive load. Okay. Highly inductive load means that when the load is very inductance is very high, suppose here very high, then suppose your current will have the wave shape like this, but because of the inductance will not allow to change the rate of change of the current, then eventually you should get a current, ID current like this if you use highly inductance in your load side. Okay.
Yes, sir.
Yes, sir.
And then it can be replaced, approximated like this, ID. So if the load is highly inductive, then we can replace the load as a constant current source. Okay. And the practical example of this one is nothing but the very heavy DC motor, large size DC motor. Large size DC motor will have the resistance very small compared to your inductance, and then it will have back EMF could be, and then we can replace the current. Since the current, if we are talking about only the current, then the output current can be taken as a constant current. We shall discuss these things now and try to find out the wave shape of the input current, all these things. Okay?
Yes, sir.
Yes, sir.
Okay, good. Here. Let me draw the circuit again. Are you following or you are sleeping?
We're following.
Yes,
Sir,
sir.
we are here, sir.
Following, sir.
Okay, you people, you are now, because you normally don't go to your sleep very early and wake up maybe late. But nowadays you have to wake up early, right? Because of your
Yes, sir.
class.
Yes, sir.
So your class is going on, right? Your
Yes,
Rulamin
Yes, sir.
sir is taking the class?
Yes, sir.
Yes, sir.
Only me has changed the class or any other teacher?
Like sir, Sia sir takes it. Isaka sir takes it
Okay.
at times when he's free. Like we discuss on the time. Like he gives us a slot. Then if we are free, we take it then. So
Okay.
yes.
Okay, so now if it is a resistive load, then you look here that this is your input voltage. And your input current will, as I told you, input current will have the wave shape like this. And okay, let me move a little here, here. And the output current, this is the wave shape of the output voltage. And you know the full wave rectifier, right? It will have the output voltage, and output current will have that wave shape like this. And if you can take the average value, how can you find out the average value? Look here, it is just showing you the average value. And they have made like this ID. So if it is a resistive load, then what will be the average value of your output voltage? Since it is a, for the half wave rectifier, we already got this one, right?
Yes, sir.
So then for the full wave rectifier, it is double. So what?
0.9, sir. Yes, sir.
0.9. So what if you want to now find out the average value of your current, then that must be your V0 by R. Then 0.9 Vs divided by R will give you this average current. You got my point?
Yes, sir.
Yes, sir.
Okay. Okay, now we are talking about the second circuit where the resistance has been replaced by current source. BSc engineering students, are you following the class?
Yes, sir.
Yes, sir.
If you have any problem or anything, please. And when I was trying to take their class in the last, which date? I forgot the date. Maybe Monday.
Yeah,
My pen was not working. Then I again reload the driver of this Wacom, and then now it is okay. And it was very, very annoying for me. I'm very sorry for that one. Okay, so this is the constant current. If I want to plot the current here, let us plot the current here. Say ID, and it is a constant value here. Then what will be the, how can I plot this IDT? What would be the wave shape?
Sir, for this, sir, it will be that two hump.
Square graph or rectangular graph.
Oh,
Rectangular? Hey, Y is
The
X.
constant.
How you plot this X and Y?
Straight line.
straight line through the origin, sir.
Like this?
Yes, sir.
Is it like this? Okay.
Yes, sir.
If it is, okay, if it is C, a constant.
So then there is a
to gradient change.
no, sir. It will be a straight
Parallel
straight
to
line,
x-axis.
straight line
Oh,
parallel.
constant parallel to X.
Parallel to X-axis. Who told this? Who told
Sabrina
first?
Saima person.
Yes, she is correct. We'll get a voltage like this, current like this. Thank you. You are following the class. So this is, then if it is ID, okay, say 10 ampere, then what will be this value? 10 ampere, right? ID. Yes. Okay. Okay, now we want to, for the positive half cycle, we are thinking about this positive half cycle, okay? Positive half cycle. So again, the same, the current should go like this, and this should come like this, and this should come back like this. Then what should be the your IS then? What should be your IS? IS is going this way, this way, this way, this way.
IS equals to the
Positive
positive half
ID.
cycle of
Same
ID.
as positive ID. Sir.
IS will be positive ID, right?
Yes, sir.
That they have plotted here. IS is the positive. And that, that means, okay, if I want to plot it here. So this is your say, this one, then your current will be IS. This is IS I am trying to plot. And this will be like this. Am I correct or not?
Yes, sir.
Yes, sir.
For the negative half cycle, then what will happen to your negative half cycle?
Current direction is opposite
Yeah,
to the ID.
right. The current will now, because the current will go, because this is negative, this is positive. Let me change the color. Maybe which color I should use? This one. Okay. The current will go this way, this way, this way. In the load, it will be same, but in the source, it will be opposite, right? The same thing what we get for the resistive load. But here, since we are getting a constant current, so it will just change the direction like this. You understand it or not?
Yes, sir.
If it,
Yes.
if it is
Yes, sir, understood.
if it is resistive, then you will get like this. Since we have the output kind of constant, so we will have a rectangular wave shape of IS. It is no longer it is sinusoidal. If you do your Fourier series analysis, then you will get one current, that is the fundamental current, which will have the same frequency of your voltage. We called it IS1. IS1 means that it will have the same frequency of your input voltage. Okay? Do you
Yes, sir.
understand it or not?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay. Okay, now let us go a little down here. So look here. So, oh, of course, your since can you listen the barking of your dog outside?
Yes, sir.
Yes, sir.
Very excited.
Very excited, but in
It is hungry.
yes, it is hungry, but
Told you that.
yeah, but in the village,
Yes.
in the village, there is a rumor like if the dog barks too much in the night, this is not a good symbol.
Yes,
Like
sir. Yes, sir.
some yes, some dangerous thing is coming.
Or some witches. Yes, sir. Or some devils.
Yes, yes.
Yes, sir.
So okay, so this is your D1 and this is your D2 and this is your D3 and this is D4. So D1 and D2 will be conducting for the positive half cycle, and your output voltage VD will be just Vs. And then in the negative half cycle, and we will see that it will be just same as the resistive load. Okay. So this, suppose this is pi and this is your twice pi, if it is omega t, and suppose your omega t equal to 0 here. And if we take the average value of this one, and you know that average value will be 0.9 Vs, right? Where Vs is the RMS value of the input voltage. And the current, we are getting the constant current here. So what will be the power then? PD, VD multiplied by ID. Am I correct or not?
Yes.
This is,
Yes, sir.
and that will be your 0.9 Vs ID. You understand it?
Yes, sir.
Yes, sir.
Okay. Okay, now I want to ask one question to you. Is that suppose your IS will have the wave shape like this. This will be your IS, and this is your say ID, and this is your minus ID. What will be the RMS value of this one if it is ID? What is the RMS value of the total?
ID,
ID.
positive ID.
Positive ID, yes. Okay. And if you do the Fourier series analysis, you will have a current that will have the Fourier series is nothing but the summation of the sinusoidal with different frequency, right? You know it.
Yes, sir.
Yes, sir.
So this is your IS1. So what is the phase difference of, oh, okay, let me also draw the voltage, input voltage. Suppose your input voltage will have the wave shape like this. The black color is, so now the zero crossing of the VS and IS1. Crossing of the VS and IS1. Is there any phase difference?
No, sir.
No, sir.
No, sir.
Zero.
So this, so we call it phi 1 phase difference, and it is 0. And cosine of phi 1 will be known as displacement power factor. Displacement power factor. And this is phi 1 is 0 here, and for our case, for this one, we see that the displacement power factor is 1. Am I correct or not?
Yes, sir.
Displacement power factor, we got 1. Good. Okay. So, and here, if I plot the IS here, like this is your IS. So they said that, okay, this is your ID. This is ID, and this is minus ID. So when VS is equal to greater than 0, our IS is positive ID, and when VS is less than 0, that means the negative for the positive half cycle. IS is ID. ID is capital ID for your case, and for the negative half cycle, this is minus ID, which is minus capital ID. Okay, you understand it?
Yes, sir.
Okay. And here now they have also found the average value, what I have already told you. If you integrate it for one, this repeating of this one, so we can integrate it 1 by pi 0 to pi, then √2 VS sine of omega t d of omega t. If you complete the integration, you will get 0.9 VS. So why this 0 is coming here? VD is the DC value with a 0. Why this 0 is coming here?
Ideal case where,
Ideal means that LS, the source inductance is 0. Okay.
yes,
The source inductance we have considered here is later we will consider if there is a source inductance, then it will be completely VD. But to differentiate this one, we put the suffix VD or VD00. 0 is the meaning of LS equal to 0, and it will then, if you do it, and it will come as 0.9 VS. You have to remember this one, because quiz question can be set. You look here the equation. Okay. Now, what I have already told you that they have written here. Now, this is very important. Again, I am plotting the IS. So this is your ID, and this is your ID, of course, and this is minus, right? This is your 0, and this is the omega t. This is your pi, and this is your price. This is minus ID, right? And I told you, if you do the Fourier analysis, we will get the same frequency This will be known as IS1, and this is your IS. Now, what is the relation between the average? Okay, the RMS value of IS. The RMS value of IS we have already told what? RMS
IDs.
IDS. So what is the RMS value of IS1? That means this fundamental value. If you do the Fourier series analysis, if you can find say IM1 means the fundamental frequency of peak value of the fundamental component, then if you do the √2, then you will get that, and it will come at 0.9 ID. So you ask me from where you can we have got it from 980. From chapter 3, if you go there, from chapter 3, you can always find this one, but I can prove it very easy way. Suppose it is a lossless conversion. Lossless conversion. That means your P input must be equal to your P output, and P output will be VDO multiplied by ID, and P in will be your VS IS 1, then cosine of phi 1 power factor. Again, I am writing VS IS 1 cosine of phi 1, and this is your VDO ID, right? So why we have taken IS1 and this power factor? Because when you write down the input power, you have to compare the same sinus. This is your sinusoidal voltage. You have to find out the sinusoidal current. But our current was not sinusoidal, so we have to take this sinusoidal IS1. You got my point?
Yes, sir.
So VS IS1, and we have already got it 1. And this VD0, we have already got 0.9 VS, and this is your ID, right? So VS cancel, and ID equal to your, okay, keep ID is this one. Now your IS1 is coming as 0.9 ID. I will not ask you to drive it, but you have to remember that for the rectangular wave shape, if this is your ID, then the fundamental component, the RMS value of this one will be 0.90% of your peak value. Okay?
Yes, sir.
Okay. I have already taken one cup of tea, one mug of tea. Still I am feeling sleepy. I don't know what is going on. Okay. So from the, if anyone is interested, then he can always find out the other harmonic components, and they have, for this one, they write down this way. Oh, let me write down this one. ISH is either 0 or IS1 by H. When it will be 0? If it is symmetric with the T axis or omega T axis, then even harmonics component will not be there. This is the properties of the Fourier series. Do you know it or not? When your mathematics teacher taught you, did he tell you some of the properties of the Fourier series? If any wave is periodic and non-sinusoidal, then it will not have the even harmonics, it will be 0. H is the number of harmonics. And the third harmonics, say third harmonics, fifth harmonics, seventh harmonics, that value will be there. How can we find out? Well, suppose we want to find out H equal to 3. The RMS value of the third harmonic component, that will be your IS1, H will be your 3. You understand?
Yes,
What
sir.
is that? What
Yes,
is
sir.
your IS1?
0.9 ID.
Right, 0.9 by 3. If you want to find out the fifth harmonic, just put here fifth, 5, 5, then you will get it. And total harmonic distortion now we want to find out for this one. Look here, total harmonic distortion percentage. We have to use the formula IS square minus IS1 square divided by IS1. Then we have already know this is IS equal to ID square, IS1 equal to 0.9 ID square divided by IS1 is equal to 0.9 ID square. So if you do this calculation, you will get this. So total harmonic distortion is coming as 48.43%. And if the input current has the wave shape of like this, what will be the total harmonic distortion?
0.
0. And for the rectangular type 1, and it is coming as how much?
48.4.
What is the physical meaning of this one? You have deviated, you have distorted the you have distorted your input current from the sinusoidal by a factor of just a moment. Okay, 48. You have distorted your input current from its sinusoidal value by a factor of 48.43%, and that is quite unacceptable. What is the limiting value? IEEE has given, okay, you can make any power electronic devices, but your total harmonic distortion must not be greater than 6%. That means you have to make this input current. Who is supplying this input current?
Utility.
Utility, PDB. So you have already distorted this one, and this third harmonics current or fifth harmonics current, particularly the third harmonic current that will flow through your neutral. Suppose you have a, this is a generator side, and you have a neutral and grounded, you'll see that third harmonic current will flow like here, and it will be very much high. And also, if there is third harmonic current, suppose in your room, and it will create a noise. Third harmonics means that 3 times frequency of your 50 hertz. Fifth harmonics means that 5 times frequency of your 50 hertz. Then your fan will have the torque. Torque will not be smooth. And also there will be humming noise. In earlier cases, the tube light, they use an inductive type, they call it choke blast, not choke blast. So it changed the di by dt, so it gives a humming sound. So all this problem is there, and the utility will not allow it. So we have to do something. A lot of researches are still going on how to make this input current as sinusoidal as possible, very much close to your input voltage. Okay. Now, let me go here. So now, this figure, it is very much, it should be now very much clear to you. This is your VS, and this one is your IS, and the dotted line is the IS1. And we have already told you that will be the formula for your fundamental component of your harmonics. Then if we write down IS by IS1, that is 1 by H. So you put H equal to 1. That means here 1. If you put H is equal to 1, what is this factor? 1, right?
1.
So that they got it 1. If you put H is equal to 3, that means third harmonics. 1/3. If you H is equal to 5, then 0.2. So look here. the component is decreasing like this. Our higher harmonics components are not very problem, but we have to eliminate at least up to the fifth harmonic or the third harmonic so that we'll have the almost sinusoidal. So what you can do when you will be doing some masters or PhD, you can find out a lot of ways to reduce these harmonics to make it as sinusoidal as possible. Okay? It is the time now. How long we are supposed to study?
Sir, 9:45.
45.
45.
9:45.
9:45. Sorry. Yes. 9:45.
9:45. Good. Now, okay, so this is your sinusoidal. How many students now? 100?
31.
31 means 130. Oh, good number of students. I'll take the attendance very soon. So don't go away. Yes.
Okay, sir.
So now, look here. Our input current, we have that. Right? This is the input current ratio, IS. So VS and IS, where VS is the RMS value of the input voltage, IS is the RMS value of the input current, and then this is your, say, power factor. Input power factor. Okay. And that will be your out power is what? 0.9 VS ID, right? Am I correct or not?
Yes, sir.
Output input power is equal to now output power, and that is equal to also say yes, input factor, input power factor will be equal to then 'That this creates always confused for me. Okay.
For the input side, it will be VS IS1 and cos phi 1.
S power factor will be your actual power, and then S equal to VS IS. Okay, and this is your say VD equal to 0.9 VS and ID, right? Yes, 0.9 ID is equal to VS. I got confused. This one also in the yesterday when I was teaching the people master's student. Let me go. There's some question in the here. Look here, the power factor is this one. So yes, here. So apparent power multiplied by power factor should be your P, and then just a minute. Go back. 3.10. Okay. We have to remember this one. Just this one. Okay. So power factor is PS by this one, then P by V1 is equal to cosine.
Yes, sir. Our real power is PS into 0.9 IS. And apparent power is PS into IS.
What is that?
The real
Apparent power is, yes.
real power PS into 0.9 IS.
Yes, IS input power factor, and that will be P, right?
Yes, sir.
And then your PS, what should we write?
0.9 IS.
Hmm?
0.9 IS. Real power.
Okay, that you try to remember this one. Let me go back and see. There is 3.10, 11. Okay, here 10. Here, okay, from using this. So we have to use this equation. Then let us go to our original equation. Okay, just hold on. Here, what we got? VS apparent power, VSIS, right? So they have used this equation where here from the visual and also this one is this one. So displacement power factor multiplied by 1. Okay. VSIS 1 cosine of phi 1, that is our power, and then ES IS power factor. Okay.
Sir, actually, I understood this part.
You understood, but I have to understand, right? You look here. It is now okay. Look
Yes,
here.
sir.
So these BS and these BS cancel, and this is our 1. So look here, and from the power is coming as then what? This power is coming, power factor is coming as what? IS1 divided by IS, right? Okay. What is IS1? 0.9 ID.
IS1 is 0.9 ID.
IS is equal to ID. Right?
ID, yes, sir.
So this one, this is cancel, and this is your power. So input power factor is coming as now 0.9. Displacement power factor is 1. So, but our target is your power factor should be as much as close to 1. So there are 2 parameters. Total harmonic distortion must be very much close to 0, and input power factor that must be very much close to 1. But for our case, if the current is like this, we got that total harmonic distortion is how much? 48.43%
48.43.
or something like that, and it is also 0.9. So our target is to make this one 0 and this one will be 1. So people are working on that one, and those who wants to do some work in future, so they will have to do this thing. So I have only 4 or 5 minutes left. Let me take the attendance, okay?
Yes, sir.
Stop sharing. Now let me take the attendance register. So up to this, I think the things are not bad. So you can have a look. Those who are very smart, these people should have a look to see how the things are going on. Okay. So BSCT, which section you will be? Hmm?
Section C, section C. All section.
All the sections, sir. The ABC, everyone, sir.
Yeah, here, sir.
So you will be BSCT will be also.
BSCT.
Here, all sections are present, sir. From section A, section B, and section C. All the
No,
sections.
no, I know that BSCT will be.
Section C, sir.
Oh, section C. Okay, so okay, I'm taking the class now. Attendance. So section C 301.
Yes,
Section
sir.
C.
Yes, sir.
Sir, 301. Yes, sir.
Okay, 303. I'm not taking everyone's attendance. Okay, don't worry. Rest of the people will get that. 303.
Yes, sir.
Okay, so 308.